17.4, Green's theorem, the second out of 4 most powerful theorems in vector calculus. What is this about? Well, number one, okay, Green's theorem, let me give you the bottom line. What is it? So we're going to evaluate a line integral using a double integral over a planar region. That's it. What is this again? What is number 2? What is this again? Another way that you're gonna love to evaluate line integrals using a double integral, because you guys are already masters in double integrals, right? You guys are gonna prove that on Thursday, right? So yes, of course. So hey, that's gonna be good review for what we're gonna do here. It's gonna be some good review for Thursday's exam. So but here's the thing. There's some limitations. Green's theorem, let me give you the first version of the theorem, because there's 2 versions. The curl version, which calculates circulation, and the other version, the divergence version, which calculates, calculates flux, all right? Flux. Well, we'll see about it. Okay, so yes, here it is. Evaluate a line integral, but instead using a double integral. But you might wonder, what's that? What's that term or that factor in the integrand? Remember, when you have a 1 in a double integral, isn't that just area? Well, actually, we will use the reverse. Use Green's theorem to calculate area of crazy pictures. All right, you'll see. Okay, so. But do you recognize that partial of g with respect to x minus partial of x or partial of f with respect to y? Isn't that one of the components of the curl? It's actually the z component of the curl. So that's why we call the curl version of Green's theorem. Because again, there's two versions of it. But I mean, what's not? Okay, let's look at the physics behind, if you will. Okay. So look at these 2 pictures. The first 2 pictures, what do we have? We have some kind of an expansion, while for the second picture we have some rotation. So the first picture, it's relating the divergence, right? It's relating dBF, while the second picture relates the curl of f, because curl, rotation, expansion, compression, divergence, right? Now, I mean, but these are examples of 2 vector fields that are, number 1, fully divergent, fully sourced, or fully sync, and number 2, the second vector, it's a vector field that it's fully rotational. There's no divergence at all. However, not all vector fields in nature behave purely divergence or purely curl, right? I mean, we have crazy vector fields that make us both of them at the same time, make us some compression or expansion at the same time that some rotation. Like, look at this. Look at this picture right here. Let me zoom it in so it's easy to see. Do you see all this bunch of vectors out of the curve, of the closed curve? See? Okay, so let's focus on one of these vectors. So, you see how this vector field, this vector in particular, you choose the right colors here. Yes, okay, so this vector casts a shadow right here. Remember shadows, projections, all right? So these vectors in yellow can be broken up into 2 components to add them together. I mean, remember the triangle method to add 2 vectors from day 1? So you add this vector field, this vector. So the shadow, which is this vector, and the orthogonal component of this vector, which is this vector. But these 2 vectors are meaningful. Did you see the direction of the vector in yellow? In which direction it's going? In which direction is it going? Perpendicular to the vector in green? Oh, okay, yeah, that's right. But I mean, with respect the whole setting here. Counterclockwise. Okay, let's be a bit. Yeah, no, that's true. That's true. Let's be more specific about the situation here.
The opposite direction of the force around us.
The opposite direction of the force around. Okay. Okay. There's more about it. I'm pretty sure you guys can get this, right? Okay. In which direction it's going? Huh? Okay. Let me pause the recording so I don't have empty parts of the recording here. Okay. Okay, so while the yellow vector is going in the direction of the tangential, that is in the direction of motion of a particle, the what's it called? The green vector is going in the direction of, well, in this case, expansion, right? So, I mean, again, going back to the previous two pictures here, the very simple cases, again. So what the bottom line here is that all these vectors have two components, two projections. So these vectors project some magnitude in the direction of motion or in the direction of circulation, and some other magnitude it's going in the direction of expansion or compression, right? So that's what we want. Yeah.
So the yellow one, can we get it green like a curve, and
the green one?
we get it with the divergence?
That's correct. That's what we wanted to summarize.
So we have to do two operation that calculate the rotation.
Well, that's why we have two versions of Green's theorem. The first version we're going to discuss. What time is it? Yeah, we have plenty of time. The first version we want to discuss is the curl version, which is also known as the tangential version because, yes, it's related to the curl. Look at this. It's the z component of the curl, and that's why it's also called the tangential or curl form. All right? We will discuss the other version later, the one that causes that we use where we use the divergence. And well, you might ask yourself, well, why in this case it's the z component of the curl? Because what do you have right here? If you have a planar region R, all right? Okay, this region R, which is described in the xy plane. We typically project these regions in the xy plane. So if you were to look at a vector perpendicular to this region, in which direction would it point? Wouldn't it point in the z direction? All right? And also, okay, let me with some perspective in the z direction. But if we look at the rotation about z, right? Because it's along the z-axis, right? So that's why we have the two-dimensional curl, which is just the what's it called? The curl the z component of the curl. All right? And again, if there's no rotation at all, well, the difference between these two is 0, and the value of the integral is going to be 0 because there is 0 circulation. All right? Okay, so let's have a look at some examples. So we have about 5 examples. So, okay, for problems 1 through 5, use Green's theorem to evaluate the line integrals. Draw a picture to represent the regions. Number 1, and notice these line integrals, how they are type 3. They're type 3 line integrals because they're written in differential form. Some garbage times dx plus some other garbage times dy, right? These are the differential version, the type 3 line integrals. And of course, we are describing C. Well, they could give us a vector value function, or they could give us some region to construct a picture here. All right, okay, let's have a look at this one. So, all right, so here's what we're going to do. Okay, so this is M. This is n, right? Instead of, let me go back. I forgot to change this. This is partial of n and partial of m. All right, because I'm using m and n. I'll show you why I had to change the letters later. All right. So, Let's plot this picture. So the region bounded below by y equals to 0, the horizontal line y equals to 0, and bounded above by y equals 1 minus x squared. Isn't that an upside down parabola? Yep. Okay, let's plot it. And well, this assumes a counterclockwise direction, by the way. I think it's in the theorem somewhere. Okay, so, all right. So this will be, come on. That's what I wanted to do. Okay, so y equals to 0. This is the parabola, opening down. That's negative 1, 1. Well, not that we care about this. And let's shade our region of integration. Oops. That's not what I wanted. Okay, so this is our region that we will label R. Now, again, another point of view of what are we doing. Remember, I started with the bottom line, right? The bottom line, again, is to evaluate a line integral by evaluating a double integral over a planar region. That's all it is. That's all Green's theorem is in mathematical terms. The physics terms, we already discussed that. Okay, so going back to the physics. So this is what we're doing. So we want to find the work done by the force field given by n and n into moving this particle around this surface, right? Now, what are we doing? So these arrows in red denote what we call the macro circulation, right? Macro circulation. That is the circulation in the boundary. But in this case, by evaluating the double integral over the planar region R, this is what we're doing. Do you see all these infinitely many points in the region? Okay, out of all those points, we have vectors, well, technically pointing out of the screen, right? But I mean, in our context, if this is x and this is y, they will be pointing in the z direction. So that's why we're computing essentially what? The curl in 2 dimensions, which is the curl, the z component of the curl, right? Or which is the rotation about the z-axis. But I mean, so use your imagination and think of these vectors like pointing out of the screen. You know, like remember what was that? I forget the name of this ride. Indiana Jones ride when they're shooting the arrows with air. Remember that part? Yeah. Okay. Think of that. Think of all those points. Okay. What's going on here? Okay. So this is a vector out of the screen, and this describes the curl at that point. The curl at that point. The curl at that point. So all that, do you see all these circulations? Those are the micro circulations. So so again, what are we doing? We're calculating the macro circulation by calculating all the micro circulations. All right? All right? Okay, let's go for it. Let's use Green's theorem to evaluate this. Okay. So, the integral of 2x y dx 2xy dx plus x plus y dy, that's equal to the double integral over the region R n with respect x minus m with respect y dA. Well, you know all about dA, right? It's how we will iterate this double integral. We may need or may not need polar coordinates. Well, actually we will. So let's iterate this integral. So that is the integral of n, okay, the partial of n, which is with respect x, which is 1, minus the partial of m with respect y, that's 2x, dy dx, and I'm going to iterate, so from 0 to 1 minus x squared. That's because the region, we're taking this region as vertically simple. So go back to chapter 16, regions, vertically simple regions, horizontally simple regions, and the limits of integration are going to go between -1 and 1. All right? Oh, come on. between -1 and 1. Okay, so what's next? All right, so this will be the integral from -1 to 1 of y minus 2 times, or rather 2xy, evaluated between 0 and 1 minus x squared dx. Okay, and again, careful, because we will evaluate these limits, lower limit and upper limit, for the y variable, because again we integrated with respect to y. If we had only one variable there, I don't need to highlight those terms. But in this case, we have a lot of variables at the same time, so we'd better do something about it. Okay, so that means the integral from -1 to 1 of upper limit, that is 1 minus x squared, minus 2x, what's that, times 1 minus x squared. Okay, do you guys agree that if we evaluate it at the lower limit of 0, that's going to give us all zeros? Do you really want to write that 0? You don't have to. Dx, all right? So simplifying the integrand from -1 to 1, that's going to give us what? 1 minus x squared minus 2x plus 2x cubed dx. And I'm not going to evaluate this Calc 1 integral. It's going to take a whole lecture. Well, maybe not that long. I'm just going to give you the result. 4/3. All right? So that is the total macro circulation, or the work done by the force. So there's many different ways to interpret these results. All right? And what did we do? Find the macro circulation by adding all those infinitely many micro circulations contained inside the boundary described by the curve. See, another way to see this, again, we calculate the work done evaluated the line integral by evaluating a double integral. That's what we did. We have time for another one, of course. Okay, now let's assess this result and see connections, of course, between what we did before. Why not? Okay. What do you think about what do you think, or why do you think we didn't get a result of 0 for this situation? Think about the vector field or the force field. Let me call that F equals 2xy, x plus y. All right. So, under which circumstances the result would have been 0 for this integral?
And x and y have to be equal?
Yes, that's one way. Mathematically, that's how we describe it, by formulas. Yes, and or another way to say this is it's about f. Okay, that's my hint. It's about f. It's conservative. If f is conservative, okay, let's check if it's conservative. So m with respect to y, that's 2x, and n with respect x, that equals to 1. These are not equal, so that means the vector field is not conservative. So that means there will be the rotation will not be 0, and the result confirms it, right? And also look at that. Aren't we evaluating this line integral along a closed circuit? If it were conservative A, what do you know about closed circuits and conservative vector fields? What's the value of the line integral under that circumstance? Would have been 0, right? You see the connections between what we just finished and this? All right. Time for a break.